And I have a great pleasure to invite now on stage Förtsch. He's the founder and the CEO of Q.Ant, a high-tech startup driving quantum technology in its wide range, not only quantum computing. And he has a background in mathematics and physics and doctorate from the Max Planck Institute for the Physics of Light. And as a scientist and an entrepreneur, he takes on the role of quantum realist, and he will guide us through the quantum landscape charged with hype and speculations. The stage is yours, Michael.
Thank you very much.
Clicker.
I need still something to switch the slides. Probably it's this device.
Probably this one. Yeah.
So then I will take this. Thank you very much. Thanks for joining this lecture. When I was a kid, I was truly fascinated by Star Trek. I was fascinated by that they seem to be flying and they have technology which seemed to be endlessly working. Maybe this was the origin when I became a techie. But on the course of years, I had to realize that some of these technologies were not realizable. They were just not realistic by the limits of physics. And I don't know, maybe some of you have also watched this series. And you might be familiar with topics like the warp drive, the transporter, the communicators, and all the rest. And if we're screening our today's technology landscape, we can see how influential Star Trek was, right? I mean, we have mobile phones, which can be considered the communicators. We have tablets, which are the personal accessible displays. And we even have tractor beams, which are optical tweezers to the experts. But the warp drive and the transporters, they will stay fiction forever. Because physics just not allow this. And when I prepared for this talk, I was thinking, oh my God, what do I say, right? And then I came up with reflecting my interest into Star Trek and found three categories. Two of them is fiction. Fiction I declare as a technology which we just cannot realize because physics is not allowing it. Vision is something physics allows it, even if it's technological hard. And to be fair, there are question marks. As we're doing all the way research, there might be still some things which we are unsure whether they're going to work or not. Now let's reflect some of the recent publications. And this is not for bashing. This is why I black labeled some of the latest news that they can't be traced back. But Q.Ant, the team, we took some time to reflect this and reflect these statements in public media versus physics and the laws which we're giving us. And we come up, if we just take the first sentence, with new advancements in error correction processes, quantum computers are on the way to replace classical computers. No. This is true fiction. Because quantum computing works different than classical computers, and classical computers are staying alive forever. Then there are some Swedish university demos, quantum chemistry simulation, and if you go into this publication, it's true. This can become really a vision because it's based on the fundamentals of physics. As well as the next one, and then we go, you can read them on yours. They're not only related to quantum computing, they're also related to quantum sensing and quantum communication. But if we come to the question marks, we declared question marks, for instance, breakthroughs pave ways to dramatic acceleration in battery design. We couldn't find an evidence that there is a connection. How quantum computers can help tackle global warming. We couldn't find any evidence that global warming can be simulated by any means on a quantum computer today. So we need to declare them as question marks, and I'm not bashing them, but I want to invite you what we can learn from the visionary aspects. And I've chosen two examples to explain you the problem with the headline and the truth beyond. The first is from quantum computing. I picked one, which we're currently also working on. It's the so-called flight gate assignment problem. In very simple words, it's basically arranging aircrafts at the gates to optimize routes of the passengers, that the whole ecosystem at an airport stays alive. Now, the headline could be quantum computing accelerates or optimizes logistics at an airport. But what has to come in between is that from the customer problem, the customer has a problem, the flights are scheduled very well, some of the flights are delayed, and it needs to be done a rearrangement that the whole system stays alive. Now, what has to be done? We need to put the customer problems on an abstraction. And there are multiple abstractions. In our case, we choose Kubo, which is just quadratic unconstrained binary optimization. I could explain this into details, not now. But we choose an abstraction, and based on this abstraction, we created an algorithm that matches our hardware. Now we have a consistent line of, from the customer's point of view to our hardware architecture, but this is not granted that we have now a speed up. And this is something where we currently are working on. So I can't put out the phrase that quantum computing is accelerating this. The only thing I can do at the moment, I can say we found a way to map the customer problems on a quantum computer architecture. So what it needs is, on the one side, it needs this mapping, and on the other side, it also needs the benchmark. Second example, it's now from sensing, it's maybe a bit easier to grasp. Sensing of biomuscle signals. The vision basically is that quantum sensors can enable us as humans by just measuring basically our neural signals, which then can be transported on artificial devices, for instance, to control prosthetics. Now, this is the vision, but is it fiction or vision? Well, we have to define an abstraction. The abstraction in our case is magnetic field sensing. We choose the abstraction. We want to read the signals out of the magnetic field. We need to find an algorithm. So what does the magnetic field tells us? In the end, the quantum sensor has the Siemens splitting, and depending on the Siemens splitting, I hope most of the experts still are in line with me. So this is always the hard part to explain. But the Siemens splitting in the end is a direct reference on the magnetic signal of the human body. And then we can map it on the hardware and choose how to basically realize this stack. In our case, we choose a diamond-based sensor. What we still owe you is the benchmark. Because there are sensors out there that are doing this job today. And we need now to prove over the next years, that this technology is better than existing ones. This is the bet. But in principle, from a technology point of view, it's feasible. This is why I call this a vision. Now, you already have seen it's quite tricky, especially the inner part. And what makes it even more difficult, that different peer groups need basically to be accountable for the individual layers. If we start from the customer problem, it should clearly be accountable from the industry. Because if our mission is to create industrial products and create economic value, then we have to define products that are of value for the customer. This is something which can be best defined from an industry perspective. If we then come to the abstraction and the algorithm layer, this is something where the science community needs to prove that the abstraction and the algorithm are in line with the customer problem. And what I mean with proof, I mean real peer review process, not just a news in any kind of public media. What I really mean by this is put your article on some kind of a journal which has a clear review process, and let the abstraction and the algorithm peer review from the science intelligence. And then on the end, we have to find ways to realize the hardware, but to realize industrial products, this job can only be done by the industry, because they have much more elaborate methods to realize cost-efficient products that can then in the end create products. Right. The second thing is the benchmarking. We can create a lot of technology, and we can match them on a lot of use cases. But in the end, we need to compete with our peers, with the peer technology. And if we go on quantum sensing, the metrics to compare quantum sensors with their sensing peers is the resolution, for example, of a magnetic field. It's the temperature or the form factor. There might be even more, it depends on the customer problem. But we don't need to invent new metrics here. They are invented and they are working in the spots where they're working, and this is exactly the point. If we go to quantum communication, it's the level of security where there are metrics out there in the individual communities. There is communication speed and communication distance. And if we go on the computing side, that's a bold statement now. I like qubits, but the metrics to compare is speed and energy consumption, because this in the end makes the difference. Can a quantum computer calculate a problem faster or ever in reasonable amount of time and be in line with the restraints of the energy that we can give to any data center? Right. Why? Why should we do this? Because take the quantum away. In the end, it's about new levels of data generation, new ways for data security, and new ways for data processing. And this is exactly why we should care about this technology. We should. This morning there was a sentence which I liked very much. It was quantum computing, in that case, is no longer a distant stream. And I couldn't agree more with this. I mean, this is why I founded a startup, right? But we need to develop this realistic and with the honesty, because it's that important to have revolutionary characters for everything that deals with data. And with this, I'm at the end of this session of my talk, and I hope there are a lot of questions coming up, as there might be some provocative statements in there. Thank you very much.
Thank you very much, Michael. So we do have probably time for one short question. Otherwise, is there any questions now in the room to Michael? I don't think yeah, there's one here, the fourth row, in the middle.
Hello. My question is about the energy consumption that you mentioned.
Yeah.
Is there any indication of the amount of energy consumption of quantum computing? There was one of the slides you said something about, was it energy saving or something like this? But at the moment, I think it's just so energy consuming that you won't save anything by using quantum computers. So what is your bold statement about that?
Okay, my bold statement here is it's too early to challenge this technology just by the energy consumption, but the vision and the underpinning vision here is that if we look on the complete computing architecture, you have, if you go just with a CPU and a GPU, you can forecast what the energy consumption of tomorrow will be. By integrating into this ecosystem a quantum computer, and the quantum computer carries out optimal jobs or jobs where this system is optimized on, this will lead to calculational advantages as well as savings of energy, because then each of these units is working at its optimal point.
Thank you very much. I invite you to speak to Michael in our networking area and discuss further questions.
Thank you.
There. Thank you very much. It was a pleasure.
Thanks for your statement.
Thank you.